Hello everyone, welcome to my presentation. My name is Yuge from Communication Systems Group in the Department of Electrical Engineering at Chalmers University of Technology in Sweden. Having introduced our paper, the topic is exploring diffusion multipaths in 5G slime. Our co-authors are either from Chalmers University of Technology in Sweden or Hyowon University in South Korea. And here, I would also like to thank the WASP program to support my work. This is a picture from downtown Singapore. Let's suppose we have a base station with many antennas on the top of this building. There is a user equipment here, also with many antennas. This is a signal sent from the base station to the user. The signals can also go over the complex propagation environment. As you can see, they can also bounce the bad objects and generate multipaths. And the question we want to answer is the following. Suppose one base station can send signals to the user. Can the user also determine its position and synchronize with the base station and perhaps find additional information like its orientation? And can we also provide the radar-like maps of the environment? So we want to solve this downlink mapping and positioning problem with 5G technologies. The picture on the right is the same as the one we had in the downtown Singapore, but more mathematical. Here we have a base station, and we already know where it is. Here, we have a vehicle with unknown position, unknown heading, and unknown clock bias. The signals sent from the base station to the user could be the left side, as shown in this green line, and those signals can also be bounced in the environment. For example, the signals can be bounced by some surfaces, like a wall, and then reach the user. But the thing is, when the user moves, where the signal hits the wall also moves. So we parameterize the surface with so-called virtual angle, which is a reflection of the base station with respect to the surface. It is fixed. So that means when the user is moving, even though the incident point is moving, but the virtual angle is still static. And here, this is what signal looks like at the user side. And this is a typical millimeter wave observation model in the literature. This PK is the send signal by the base station, and each channel is described by a channel gain, a response vector at the receiver, which depends on the angles of arrival, and also the response vector at the transmitter, which depends on the angles of departure, and also the delay. At the receiver side, you can have this kind of combiner, which basically makes the receiver listen to a certain direction. Given the observation, YT, and the knowledge about the sent signal and the combiner, the channel estimator can recover the geometric information, like the angles and the delays. Given those angles and delays, we then need to figure out what is the vehicle state and also map the environment. For the vehicle state, it usually contains 3D position, heading, clock bias, and maybe other information like speed or turn rate. It has a non-dynamic model, which could be a constant turn rate model or others. For the map, we at least need to know the landmark positions, and sometimes it is also necessary to know the type of landmarks. For example, sometimes we need to know the south is a very rough surface or a very smooth surface or just a medium rough surface. And now the challenge is that we don't know which measurement is from which object. So we have a bunch of measurements. We know those are from landmarks in the environment, but we don't know which measurement is from which object. For example, we don't know which one is from the base station directly, which one is from a small object, and which one is from a surface. In order to solve this question and use the received 5G signal to localize the user and also reconstruct the map of the environment, we basically need to follow this framework. We need to do channel estimation for the received signal to have those delays and angles. And because each landmark could give us more than one measurement, so that means we need to group the delays and angles based on the different sources. Here in this paper, we will not focus on the channel estimator, and we further assume the measurements have already well clustered according to landmarks. And we follow the Black-Wymeersch method. That means we use a list of particles with weights to represent the user state. And there is a map of the environment conditions on each particle. And every time step, the SLAM filter uses the motion model, channel estimators, and the likelihood computations to estimate the user state, number of landmarks position, and their types. The likelihood function is very important in SLAM filter. We use it to update the landmark state and distinguish a type. We have different likelihood for different type of landmarks. For example, we have the smooth surface. That means the surface only reflects a signal. Every time step, there would be at most one strong specular path with reserved delay and angles. As it is a specular path, we can find the incident point on the surface. That means we can compute the true angles and the delay. Then we can compute the error distribution based on the simulation. For those rough surfaces, the surface can not only reflect but also diffuse signals. So each time step, there may be more than one path reserved. The things for the specular paths, we know the incident points on the surface, but for the diffuse multipaths, those incidence points are just some random points on the surface. We do not really know where they are, so we couldn't know the real angles and the delays. But they still contain some geometric information. In order to use all those paths, for the specular path, which is the first arrival path with the shortest time of arrival, we know where is the incident point. We do the same thing as the path for the smooth surface. But for the others, we do not know the incident point, but we know those points are on the surface. So we estimate the incidence points from the measurement and compute the distance to the surface, and use this as the new measurement. Ideally, it should be zero, but due to some error and interpath interferences, it is not zero. And then we can compute the distance error distribution based on the simulation. Then the entire likelihood function has three components. The first part is the distribution of the number of paths conditioned on the type of the source, and the distribution for the specular path or the first arrival path, and the distribution of the distance for the diffusion paths. All these three distributions can be obtained from simulation of any channel estimator. This figure shows our simulation environment. There is a base station as a triangle here, and 4 different surfaces, with the virtual anchors are located at least 4 stars. And the vehicle drives around the base station with a constant turn rate. The transmitter and the receiver are both implemented with an 8x8 antenna array. The SLAM filter is based on the PMBM filter. More details about the filter and the parameters can be found in our paper. We studied the likelihood function. We place the vehicle on different positions and run simulation many times, collect the measurements, and then study the distributions. Those figures are the distributions of number of paths, delay of the first arrival path, and the translated distance of those diffusion paths for a very rough surface. And we could say that every time step, we can receive at least 4 paths from this very rough surface. And the delay of the first arrival path is more than the true value. And also, the estimation incident points of those diffusion paths are more likely to be behind of the surface. The reason is that the interpath interferences makes the delay larger. And this table shows an overview of likelihood functions for all landmark types in our simulation. This movie shows how our SLAM filter maps the landmarks. At the very beginning, the vehicle just knows where is the base station. There is no other information about the map. Each time step, measurements are generated, and the vehicle uses them to determine the sources of these measurements. Over time, as the vehicle goes, it can keep localize itself and also map the landmarks. This is just an example to show our result. Then we move into the numerical evaluation of the results. We use the so-called Gauss-bar distance to evaluate the mapping result. It is a distance that considers all the estimation error, misdirection, and also the false alarm. we compared two algorithms, the SLAM filter using all received paths in every cluster, which is our proposed algorithm in this paper, and also the SLAM filter only use a single path in every cluster. Firstly, we use the real vehicle state and only study on the mapping result. We could see that both two algorithms perform similar in mapping the smooth surface, because the very smooth surface only have one specular component. So that means the likelihood functions of two algorithms are the same for the smooth surface. And we could also find that the algorithm using all paths performs better in mapping interrupt surface and also the very rough surface, as the solid lines are always lower than the dashed lines. The reason is that more paths always provide more information. So overall, we could see that the first algorithm performs better than the second algorithm. Then we also studied the positioning result. So we added some biases to the initial vehicle state and used 2000 particles to represent the state. We found the error between the estimate state and the real state converges after 2 time steps. And the first algorithm performs better than the second algorithms in positioning, as the absolute errors are smaller. This is also because of the first algorithms use all the paths, both specular paths and the diffusion multipath, and more paths provides more information. Then conclusions. Our conclusions are as following. Firstly, diffusion multipath provides mapping and positioning information, and then the proposed scheme can accurately estimate the number of landmarks, their types, and positions. And also, using more paths provides more information. So that means using all paths in each cluster performs better than using single paths in each cluster. And also, the proposed scheme can handle mapping and the vehicle state estimations simultaneously. And recently, we wrote another paper, which is about the overview on the 5 line. It is also an extension work of this paper. You can find it online. That is all my presentation. Thank you for your listening. And is there any questions?